All right, the next two videos are some applications, but realistically, you kind of already know everything you need to know for the whole section. So if you want to try to get started on these without watching the video, go ahead. Otherwise, here are some problems. So we have a colony of fruit flies, some kind of experiment maybe. And they're exhibiting exponential growth, which means that they grow at a rate proportional to their size. It makes sense. The more fruit flies we have, the more they're going to populate. Up to like some like ecosystem restrictions, right? There's not, we can't have billions in like a little tiny area, but let's just say they have enough room and food and stuff like that. And this is how populations usually grow. The more people you have, the more people you're going to get. Suppose that initially there are 500 flies, and let P of t represent the number of flies after t days, and our growth constant is 0.08. Write the differential equation and initial condition. Remember, exponential growth. Exponential growth is that theorem y prime is equal to k times y. And here, the growth constant is 0.08. This is our differential equation. Our initial condition is when t is equal to 0, how many flies do we have? When t equals 0, we have 500 flies. We've got a nice differential equation. We've got a nice initial condition. We've got a nice answer for part A. Easy as pie. Do part B. Find P of t. Well, the solution, right, y prime equals ky, is when y equals c times e to the kt. But it's not y anymore, it's P of t. We can call this function whatever we want, so let's call it P of t equals c. Note that actually we could plug in 0 for t, but in this form, c will always equal y of 0. Right? Every time we plug 0 in, this will become 1, and then we'll just have c. So c is going to be y of 0 kind of always for these problems. Can take a little shortcut, and it'll be 500 times e to the k, which is 0.08, times t. Part B, done, just like that. All right, and in general, you may also see this formula. I'm not going to introduce this as a separate formula because it really is the same thing we've been doing. But the book may write P of t equals P naught, P sub 0 is the initial amount, e to the kt. It likes to use that, but you can use y's and c's just like before because it is the same stuff, just with different letters. All right. So here we have right here, according to the assumptions in the problem, the answer to part B. Part C, estimate the size after 5 days. So all we're going to do is use our population model, right? We have that our population model is 500 times e to the 0.08 times t. Well, after 5 days, that's just a value of t, right? T is number of days. So we just plug in 5 for t. And we'll get P of 5 equals 500 e to the 0.08 times 5. Plug that into a calculator, and you should get that it is approximately equal to 500 times e raised to the 0.08 times 5. 745.91. So we're going to say about, we're not going to talk about fractional fruit flies. Fractional fruit flies, kind of hard to say. 746 of them. All right. Look, we can even draw some fruit flies. All right, fruit flies are kind of hard to draw with a fat pencil on a tablet. But those are my fruit flies. They kind of look like V's. And that's honestly most of the video. I'll do another example for a little bonus. But that's basically what we have. We've already done all the math in the previous video. Example 3. You know what? I'm going to type this one out actually, because I'm lazy and don't like writing things down. Example 3 says, find the growth constant for a population, not a population, a population growing at a rate proportional to its size that triples every 10 years. Okay. So there's a lot of stuff going on here. Wait, find the growth. All right, really typing is not my strong suit either. Find the growth constant for a population that's growing at this rate. So growing at a rate proportional to its size, again, this right here, that just means that y prime is equal to a constant times y. Okay? So again, that immediately tells us that, okay, y is going to be ce to the kt. Do we have an initial condition? No. Do we have a k? No. But we do know that it triples every 10 years. So I don't know how many it starts with. Right? Y of 0 equals some c value. But we don't know c. But we know it triples in 10 years. So after 10 years, I don't know what it started with, but after 10 years, I know it's tripled. Whatever we started with, after 10 years, it's 3 times as much. We're going to use this to solve for k. So after 10 years, the y value is 3c. After 10 years, the t value is 10. We'll solve this. So we'll divide both sides by the c. The c just cancels out real nice. We're left with, we're left with 3 equals e to the 10k. We have to natural log both sides to cancel out that e. Remember, they are inverse functions. We'll get that the natural log of 3 is just equal to 10k. So k will just be natural log. K will just be the natural log of 3 over 10. Excuse me. All right. So our growth constant is the natural log of 3 divided by 10. Remember, the 10 doesn't go inside the natural log. There's a price to be paid to get inside of a natural log, and the 10 is not willing to pay it. So you can have this as your final answer, or you can get the decimal approximation, which is going to be the natural log of 3 over 10, about 0.1099. 1099. I'll take either form. Okay. There we go. This is what's known as the tripling time. The time it takes to triple is 10 years. The doubling time is very similar. It's just the time it takes to double. So this is the tripling time. 10 years. The doubling time, I don't know, maybe it's like 7 years or something. There we go. Good luck. Bye-bye.